Okay, so let's get started on the Smith chart. So tonight's going to be a lesson in electronics engineering. Sorry to do that to you, but I think I'm hoping that you'll find it interesting. I also have a little laser pointer here. I'll point out to you. Uh, I'm going to use it a little bit. If you have a question, unmute and holler at me, right? Go ahead and interrupt. I handle that well. In fact, I prefer to do it that way. And this is just a little review about what we can do with the Smith chart. But the object here really is let's take this confusing magic, if you will, and make an explanation for it. And basically what the Smith chart does is it gives us kind of a visual picture of what's happening in the transmission line itself. All right. The last time we talked about power factor, and we talked about things like reactive power and applied power or real power and apparent power, and we like to illustrate that with this glass of beer. The liquid beer there is the only thing that'll get you drunk. That's the real beer. That foam on top, well, it just takes up space. Doesn't really do anything for you unless you like the taste of foam, and I don't really know of anybody that does. It just makes it look neat, but it's otherwise useless. It does do something else that's even more useless, is it creates more losses. Then there's this apparent power. That's the total of the whole thing. Well, what we're dealing with in the Smith chart is looking at how reactive impedances affect the signal that's going through the line. So analogous to the resistance, or analogous to the real beer, to the real power, is resistance. That's what we want. We want the antenna to be totally resistant, because that means everything goes to the antenna and something good happens with it. Now, it could be a loss still. So you may have resistance out there that's just creating heat. You've got reactive power. We also, analogous to that, have the portion of impedance called reactance. That's the imaginary part, but it isn't really imaginary. It's real. It's nasty. And then the combination of the resistance and the reactance is impedance. Okay. My SWR is less than 1.5 to 1. I really don't need to do anything with it. Okay. That may be true, but no matter how low your SWR is, your radio may be happy with it, but just because your SWR is low doesn't mean you're radiating, because reactive power doesn't radiate. It circulates, and by the way, ends up as losses. So here we've got one that we worked out the last time, where we've got a transmitter with 100 watts coming out of it. I think we had 100 feet of RG8 here. And at the particular frequency we chose, we had, I think it was 1.36 dB of loss. And that means that we lost all but 73 watts to this point right here. That was just basic losses in the transmission line. Now, unfortunately, because this particular impedance at the load is 32.5 resistance and minus 30 ohms reactance, it's capacitive and it's quite reactive. And so it sets up 17.44 of our watts as reactive power that just simply circulates in here and doesn't get out on the line. Bottom line is, of the 100 watts that we start out with out of the transmitter, only 45.65 watts gets to the antenna. And that doesn't necessarily mean that it's transmitted. It still could be losses in the antenna. You could have resistive losses to the ground. You could have resistive losses in the wire because you use too small a wire. nevertheless, only 45.65 watts actually gets to the antenna itself. The good news is power factor is determined strictly by the load. So all we really need to do is, assuming that we've got transmission line that matches the output of the transmitter, all we really need to concentrate on is this part that I'm marking right here, where I've got 32.5 minus J 30 ohms. That's where we can focus. So what would happen then if I were to go in and create a stub out here that eliminated that capacitive input? And with that stub, I actually got rid of the reactive portion of the interface. So now I've got 32.5 ohms resistive as the termination. That changes my, I'm sorry, I lied earlier. It was a 2.13 dB total SWR, but just changing that part changes the SWR at the load to 1.85. Due to losses in the feed line coming back to the transmitter, we'll see 1.78 at the transmitter. But look what that does. Look what that does to my power that's available to the antenna. It goes from 44 watts to 65 watts. Makes a huge difference. So this is a big change that we can have. Now, what would happen if I could change this to 50 ohms? If I could change this to 50 ohms at J0, then the SWR would change to 1.53. Now I've done something. Question is, how do I get there? Well, let's talk a little bit about SWR. And I just want to point out a couple of things about SWR. This little P down here, that's actually the Greek letter rho, the lowercase letter rho, and it stands for reflection coefficient. And I got to move this over and read my note. Hang on a second. This is a pain. Okay. So the voltage standing wave ratio is the ratio of the maximum peak voltage anywhere on the line to the minimum value anywhere along the line for a lossless transmission line that's at least a quarter of a wavelength long. The ratio of maximum to minimum current, or ISWR, is identical to the VSWR. This reflection coefficient is the ratio of the voltage or current in the reflected wave at any one point to the voltage or current in the forward wave at that same point. And it's a complex quantity. That means it's got real and imaginary parts. It's got resistive and reactive parts to it. All right, so I can actually calculate, if I can measure my reflected power and my forward power, then with this little formula right here, I can calculate my SWR. And I can tell you back in the 70s when I was in the Air Force, that's how we did it. We got our little power meter and the little slug in it, and you pointed the slug one way and read the power, and you turned the slug back the other direction and read the power, and then we just had a little nomograph on there where we could actually, it on an analog method actually did this calculation for us. And later on, when I got a snazzy calculator that I could program, I could put the reflected and the forward power in it and got my SWR. Kind of neat and spiffy. One other thing that we can do, since we've got these antenna analyzers, I can go to my radio and I can measure what the actual impedance is at the radio. Then using my Smith chart or some of these software programs that, and I'll show you again at another time, some of these software programs that will take and eliminate the coax or the feed line, whatever it is, between the antenna. It's just going to do it mathematically and calculate exactly what that SWR is at the antenna. So here I can take and I'm sorry, calculate this, calculate the impedance at that point. So here I'm showing two impedances. This ZL is the impedance at the load. L stands for load. This ZO is the characteristic impedance of the coax or the feed line, whatever it is. So in this case, I would take this complex impedance and divide it by this complex impedance, and that's my SWR. And so I can calculate the SWR. I can do this with a Smith chart. Now, all right, so I've got a tuned stub here that I've switched to 50 minus J0. Notice that my reflected power is virtually nil now. My SWR at the load is essentially 1.0 to 1. So the SWR at the generator or my transmitter is going to be essentially or effectively or virtually about that same amount. It'll be a little different because the coax isn't perfect, but it'll get us real close to that. Well, that means virtually 100% of the power output is real power. It's applied to the antenna, but there's still going to be resistive losses. So I'm going to have resistive losses in the feed line. Just because there's copper there, RG58 is going to have a lot more resistive losses than RG8. I'm going to have ground losses. I'm probably going to have some other resistive losses that occur as a result of, believe it or not, capacitive coupling between the legs of the antenna and ground. So how do I actually calculate the required R plus JX that I need here to get to this point? And as much as anything, that's what tonight is about. How do I get this? How do I figure out what I've got to do? I'm going to use the Smith chart, but I got to know what number I need to get get the Smith chart to tell me how long my piece of coax or feed line needs to be for this tuned stub. So I got to do a little arithmetic. Sorry, guys, I can't avoid it. All right, so here's our goal. Using a Smith chart, we want to design a matching network to correct the power factor. It can be an L filter, a double L filter, a T filter, whatever. Might just be a long or maybe not so long piece of coax. And that piece of coax can be either in series or parallel to the antenna feed point at the feed point.
The stub is not terminated, right? It's just nothing at the other end.
Not necessarily. That's another subject altogether. Is it terminated or is it left open? That's going to depend on some things. So I've still got a little studying to do on that one yet, Dave. But it could be either one, depending on how long it is. Okay, so that means we've got to talk about duals. And I'm going to tell you that you're probably more familiar with duals than you think you are. But since our stub is going to be connected to the antenna in parallel with a transmission line, and that's real easy to do because all you need is an SO239T connector. Since it's going to be connected to the antenna in parallel with a transmission line at the antenna, determining the design of the matching arrangement is simplified if Smith chart values are dealt with as admittances rather than impedances. An admittance is simply the reciprocal of the associated impedance. And this is more easily understood if we're introduced to the idea of duals. So plotted on the Smith chart, the two associated points are on the same SWR circle, but they're diametrically opposite each other. And I'll show you that here in just a second. But using admittances leaves less chance for errors in making calculations. It simplifies it by eliminating the need for making series equivalent to parallel equivalent circuit conversions and back, or else for using complicated equations for determining the resultant value of two complex impedances connected in parallel. Now, I will say that a lot of this is dependent upon this thing being, doing things manually with the old manual chart. And you're probably eventually not going to do that. You're going to grab a software program that somebody else has already done, unless you're the guy that's going to do the software program. All right. So let's talk about duals, because forming the dual of a statement consists of replacing each electrical term with a term of opposite meaning. So let's start out with, this is a Smith chart. This is the center point right here where we normalize to. And normally this is off on your left. This would be the top. This would be the bottom. If you look closely over here, you'll see right here that this is inductive reactance component going this direction. The resistive component goes this direction. These curved lines here represent the inductive reactance component, or what's known as the capacitive susceptance component. I'll get a little more detail on that in a second. On the opposite side of that, you've got the capacitive reactance component or the inductive susceptance component. Notice how they're just on exact opposite sides of the resistive line. Okay, so here are some duals. If we start out with duals, the dual of series is parallel. And I can have two equivalent circuits, one that appears series and one that appears parallel, but they're actually identical circuits. The dual of resistance is conductance. You're probably familiar with the term mutual conductance tube tester. Conductance, resistance tells us how much resistance there is to the flow of current. Conductance tells us how much current it'll allow to flow for a given voltage. So they're basically the reciprocal of one another. Reactance has a dual called susceptance, and impedance has a dual called admittance. Then inductance has a dual, which is capacitance. Voltage has a dual, which is current, and a voltage source has a dual, which is a current source. So let's look at a couple of duals. Here is a series parallel resistance circuit, and here is a series parallel conductance circuit. In the resistance circuit, I got a 5-volt source. In the conductance circuit, I've got a 0.625 amp current source. Here I've got a series resistance. And it's 4 ohms. The reciprocal of 4 ohms is 0.25. So here, instead of R1, I've got conductance 1 or G1, and it's 0.25 mhos. Notice that the ohm symbol is upside down. Now, that's politically incorrect today. The IEEE, I guess, is the ones that did this, but they decided that instead of calling it mhos, we should now call it Siemens, named for one of the early pioneers in electronics, named of all things Siemens. Just like back in the 50s and 60s, frequency was in cycles per second, and then in the late 60s, early 70s, we changed that to hertz after Mr. Hertz, the famous pioneer early on. These two circuits are absolutely identical. They behave in exactly the same way. And I can do any engineering work that I need to do to either one of them, and it'll work either way. Here I'm showing conductance is equal to the reciprocal of the resistance, or 1 over the resistance, so G equals 1 over R. Susceptance equals 1 over reactance, or 1 over X. And acceptance is 1 over impedance, or 1 over Y. Oh, I'm sorry, 1 over Z. So I've got G for conductance, B for susceptance, and Y for acceptance. You'll forget this, so don't worry about it. You can look it up somewhere. But I want to talk about how you do some of this. Notice that all of these, there are reciprocals. So one of the things we're going to have to learn how to do is, how do I take the reciprocal of 50 plus J0, or how about, was it 30 plus, or 30 minus J32, or whatever that number was. Yeah, it was 32.5 minus J30. That was what we calculated we had actually out at the antenna. I'm going to need to be able to take the reciprocal of that. So here is an example of it. I want to calculate what the actual resistance is of these 3 resistors in parallel. I have a 5 ohm, a 10 ohm, and a 20 ohm. How do I calculate what that resistance is if I measure it right here? Well, I could always grab my trusty flute meter and measure it, right? Well, that's not really very practical most of the time, especially not when it's reactive. But I could take and convert each one of these to a conductance, which I've done here on the denominator of this equation. So G1 is equal to 1 over R1, G2 is equal to 1 over R2, and G3 is equal to 1 over R3. I can just add those three together in series. Then I have my total conductance, but conductance is equal to 1 over the resistance. So if I just take the reciprocal of conductance, I'll get the resistance, right? It's that simple. I can do the exact same thing with my complex number. And that's what we'll learn how to do. Now, here are three separate examples. Here's a transmission line with a load on it. So this is the transmission line and the load. I can display this as a series equivalent circuit of this transmission line, or a parallel equivalent circuit of that transmission line. All three of these are the same. And this, by the way, is in the ARRL antenna book. And it includes equations here for calculating, actually converting between parallel and series equivalent circuits. Now, the reason why this is important is some of these antenna analyzers will actually tell you what the series or parallel resonant circuit looks like. It'll give us the inductance or capacitive reactance and resistance. It will actually show it for you, and even the little card that I've been using from Rig Experts on your computer, it'll give you both series equivalent and parallel equivalent. So that information's available to you. All right. Now, just so we've got this in an analogous mode, I've got my conductance and resistance. They're the ones that are going to get us drunk. That's where all the work is done, right here, the liquid. So the conductance and reactance are analogous to one another. The reactive part, the imaginary part, the susceptance and reactance are analogous to one another. That's the foam. Won't do anything for you except it takes up space. And then the combination of the two, which is the acceptance and the impedance. So we're going to be talking about the combination. So I'm going to have, let's see, what am I doing wrong here? Okay, so I'm going to represent these numbers as conductance or resistance plus or minus J, reactance or susceptance. Is everybody keeping up with me so far? Okay. So we're going to need to do a little complex arithmetic. It's really pretty easy if I'm doing addition and subtraction. If I wanted to add A plus JB, so A is the real, B is the imaginary part. I want to add that to C plus JD. All I have to do is add A to C and B to D. That's it. So if I were to add 3 plus J4 to 5 minus J3, I get 8 plus J1. Does everybody see how I did that? Everybody can do this, right? Subtracting is basically the same way. I'm going to take A minus C. So I've got A plus JB minus C plus JD. So I'm going to subtract the real part, C from A, and I'm going to subtract the reactive part from the other reactive part, so D from B. So A minus C plus J, B minus D. So now 3 plus J4 minus 5 plus J3 equals minus 2 plus J7. Everybody follow? The reason I did a minus here is because I've got I'm always doing this in A plus JB. The reason I did that this way was I've got a minus and a minus. Minus minus a minus is what? It's plus, right? Okay, I just want to make sure we got that. It's just kind of simple math, but we tend to forget those things. Okay, now another way of representing this number is in what's known as a phasor. And what we've got here with a phasor, I broke it out. The real portion that we're calling A is on this horizontal axis off to the right. The imaginary portion is the B axis, the vertical axis. It's inductive going positive. It's capacitive going negative. A phasor basically takes, in this case, I've got 3 plus J2. Can you see that clearly on the screen? 3 plus J2. The hypotenuse of this right triangle represents the magnitude of my phasor. Everybody remember Pythagoras' theorem? A squared plus B squared equals C squared, or C, in this case R, the hypotenuse is equal to the square root of the sum of A squared plus B squared. That's my magnitude. This was really hard. The hard part is I got to get my calculator out and find the arctangent of the imaginary part divided by the real part. So this angle theta here is the arctangent of imaginary over real. So 3 plus J4, if the square root of 3 squared plus 4 squared, the square root of 9 plus 16 is 25. The square root of that would be 5, right? 4 divided by 3 is 1.333. The arctangent of that is 53.12 degrees. Now, this is on your extra exam. Not these particular numbers, but there are going to be several questions on there that could ask you to convert this value to this value and vice versa. So if I do this as 5 minus J3, I come up with the same thing, a 55.83 at an angle of minus 30.96 degrees. Is that one capacitive or inductive?
Capacitive.
It's capacitive. Thank you. Now, what if I want to go from polar or from a phasor back to rectangular or Cartesian coordinates? A, the real part, is the magnitude R here times the cosine of that angle theta. The imaginary part is R times the sine of that angle theta. These are three formulas that you really need to memorize, or else have a calculator that'll do the work for you. All right, so how do we do multiplication and division? Let's multiply 3 plus J4 times 5 minus J3. So this one's inductive, this one's capacitive. We start by converting it to polar notation, or we convert it into a phasor. So converting 3 plus J4 to polar notation, remember we did that on the previous screen. It's 5 at an angle of 53.12 degrees. 5 minus J3 is 5.83 at an angle of minus 30.96 degrees. So what I'm going to do now is I'm going to multiply these two magnitudes together, and I'm going to add these two angles together. So 5 times 5.83 is 29.15, and 53.12 degrees plus a minus 30.96 degrees comes to 22.16 degrees. Make sense?
Yep.
All right. Now, if I convert this back to Cartesian coordinates, I convert this to the A is 27, the B is 11, so 29.15 at a cosine of 22.16 degrees is 27. 29.15 times the sine of 22.16 is 11. And didn't I get that earlier? No, never mind. I'm sorry. I'm getting dizzy. I'm smoking dope. All right. If I want to divide it, the difference here is instead of me multiplying these two magnitudes together, I'm going to divide them. So I'm going to divide 5 by 5.83. And instead of adding these two angles, I'm going to subtract them. So 5 divided by 5.83 is 0.858. And 53.12 degrees minus 30.96 degrees is 84.08 degrees. Dividing it now, this becomes inductive, right? And if I convert it back from polar to rectangular mode, or from a phasor to a simple complex Cartesian coordinates, I get 0.0885 plus j 0.0853, which is where we started. Okay. We need to be able to take the complex conjugate. Now, the complex conjugate essentially is the same number with the opposite sign on the reactive portion or on the imaginary portion. So if I want the complex conjugate of 3 plus j4, that would be 3 minus j4. Keep your finger there because we're going to use this one. And I also said that we were going to need to be able to take a complex reciprocal. So if I'm going to take some impedances in parallel and add them together easily, I need to turn them, first of all, into an admittance. To do that, I take my impedance and I take the reciprocal of it. So to get there, the first thing I'm going to do, so here I'm showing the complex reciprocal 1 over the complex number 3 plus j4. First I'm going to do is convert it to polar. So I'm going to convert the 3 plus j4 to polar. So now I've got 1 over 5 at an angle of 53.12 degrees. This one's hard, guys. I take 1 over the 5, that equals 0.2, and I switch the sign on the angle. So it goes from positive to negative. That's it. That's all there is to it. So now if I want to convert it back to rectangular, I go back to this 0.2 times the cosine of minus 53.12. That gives me 0.12. Or then I've got 0.2 times the sine of minus 53.12. So that gives me minus j 0.016. And now I've got the reciprocal. So I've got the complex conjugate and I've got the reciprocal of that number. Now, this is just a little cute fun. We call it operator J. Everybody else in the world calls it operator I for imaginary. But in the electronics world, we already had something for the little I. That was AC current. So we use operator J, and operator J equals the square root of -1. What single number multiplied times itself? All right, back up. What single number multiplied times itself equals -1? Doesn't exist. There isn't one. That's why it's called an imaginary number. The funny thing is, though, is that it works just like a real number. So if I take the square root of -1 and square it, so the square root of -1 times the square root of -1, what do I get? -1, right? So j times j equals -1. -1 times 1 equals -1. -1 times -1 equals 1. Okay, so watch this. I'm going to multiply these two in Cartesian coordinates and utilize the square root of -1 and watch what happens to the numbers. So I'm going to multiply a plus jb times c plus jd. So a times c plus a times jd. Follow me? jb times c plus JB times JD. So A plus C we can represent as A times C is here, just got AC plus, if I simplify these two, I've got operator J times A times D plus B times C. Now, what is J times J? Minus 1. So I've got now AC plus J times AD plus BC minus BD. Now let's do it with real numbers. So I've got 3 plus J4 times 5 minus J3. So now I've got 3 times 5, which equals 15. I've got minus J3 times 3, which equals minus J9. I've got plus J4 times 5, which equals J20. Now over here, my J4 times minus J3, I've got J times J, which equals minus 1, right? But this one is a minus, so I can multiply that times minus 1. And then I've got times 4 times 3. So that means minus 1 times minus 1, minus 1 times minus 1 equals positive 1, times 4 plus 3. So now it equals plus 12. So now I've got 15 minus J9 plus J20. That simplifies to J11, right? Plus 12. 15 plus 12 equals 27. So multiplying those two numbers together, I've got 27 plus J11. Isn't that the number we got earlier by converting it first to phasors and doing the multiplication? I just think it's cool and kind of fun because the square root of minus 1, even though it doesn't exist, it works like a real number. How about if I divide it as Cartesian coordinates? So to divide 3 plus J4 divided by 5 minus J3, I start by making it a ratio. So I've got 3 plus J4 over 5 minus J3. And the complex conjugate of 5 minus J3 is 5 plus J3. Now, this is an old algebra rule. If I multiply both the numerator and the denominator by the same number, I haven't changed the ratio at all, have I? But if I'll multiply the numerator and the denominator here both by the complex conjugate of the denominator, then I make the denominator purely real without changing the value of the ratio. So now I multiply 3 plus J4 times 5 plus J3, and I get 3 plus J29. Multiply 5 minus J3 times 5 plus J3, I get 34. So now I've got 3 plus J29 divided by 34. So 3 divided by 34 is 0.0882. And J29 divided by 34 is equal to J.853. Ain't that the same number we got when we did it as polar or phasor coordinates? Kind of cool, isn't it? All right. Now, there's a couple other things that you could do. You could use a calculator that's already got this capability built into it. I've got this HP 50G graphing calculator that does all this stuff for me, man. I mean, it's just slicker than owl snot. Or if you don't have one of those, I created one for you. So this was available for you to, it's on our groups.io for you to download. Did anybody download this? Okay, so here's just it should even run on your iPad or on any phony baloney computer from the fruit company. I'm sorry, make-believe computer from the fruit company, because I'm not doing anything special in Excel. So it should run on any Excel platform that you got. Notice up here at the top, it says data entry and it's background in blue and result is background in yellow. So you can enter values here in the blue. So over here I have the real part, over here I have the imaginary part. And by entering these this number here, real and imaginary, it'll actually give me over here on the right the polar coordinates. So 35.84 plus J 9.38 is equal to 37.05 at 14.67 degrees. So if I want to put, well, let me get back up here to the top. I'm sorry, I was really messing up. I was in the wrong place. Here I've entered 10 plus J2. I get a reciprocal of 0.1 plus J minus 0.02. And polar notation on the right. If I want to convert from polar notation back to rectangular notation, that's where I go, where I'm at right here. Can you see my cursor? Okay. So if I've got a phasor that's 6.4 at 38.7 degrees, so I enter here and then here, then that automatically calculates for me over here on the left, 4.99 plus J 4.0. So you can do polar to rectangular conversion. Enter anything up here, it'll convert it to polar. Enter it down here, it'll convert it to rectangular. Enter it here in rectangular, and it'll give you the reciprocal in rectangular and in polar. Here it'll add A plus B. So 12.5 plus J 37.5 added to 48.6 plus J 17.5 gives me 61.1 plus J 55. And again, over here on the right, it's the same thing in polar notation. How about subtracting B from A? Same things right here, works exactly the same way. Here I've got A times B. So 1.4 plus J 33.2 times 52.1 plus J minus 0.11. That's the same thing as saying 52.1 minus J 0.11, right? That gives me 73.29 plus J 166.57. Next one is I'm doing the quotient. So I can enter it in Cartesian coordinates A divided by B, and it gives me the quotient. Now, how about if I've got two impedances in parallel? I put one impedance here, another impedance here, and it'll calculate the parallel impedance for the two right here. Now I'm gonna play a little game with you right here. Remember on our last diagram screen, we asked the question, what do I need to calculate? What number do I need to go to the Smith chart with in order to make that figure, make that impedance at the antenna 50 plus J0? That's what this last little block here is for. I had 32.5 minus J30 or plus J minus 30, right? So that's what I actually have calculated at my antenna. My coax is 50 plus J0. I enter that down here in the blue, and it says the number I need to get is 13.73 plus J 62.18. That's the number I'm going to want to work on our next presentation on the Smith charts. That's the number I'm going to want to try and incorporate into my shunt. And so knowing where to put that spot on my Smith chart, then I'll be able to work around how many degrees in length and whether it's opened or shorted at the end of my coax or twin lead or whatever it is I've got. Now, just for grins, let's see, if I put up here 32.5 plus J minus 30, and then I get down here and I enter 13.73 plus J 62.18, then it should calculate for me down here 50 plus J0, right? So there's your calculator. Let's close this. I'm going to don't save. And this is my calculator that does all that work for me. I actually even have yeah, you got one too. Yeah, okay, so yours does it too. These calculators are easier to use than the spreadsheet because, well, calculator's small, I'll hold it in my hand. It's a little more of a straightforward arrangement.
Well, you can take the calculator, but you can't take a spreadsheet on the exam.
That's true. That's true. Good point. Okay, questions. Did this make sense? Was it a waste of time?
I enjoyed it. Thank you very much, bud.
Okay. Questions?
Lots of questions, but I know where the stuff's coming from because I know what you're talking about. And I've seen all that stuff, but it didn't make sense how to get from one to the other. And by the way you took it through, showing how to convert different ways and do different ways of math, now it makes sense what they're trying to do with it. Still makes my brain hurt, but.
And when we get done with the Smith chart, you may never use the Smith chart again because we've got these software packages that'll do all that for you. But the Smith chart is the way to learn it because it gives you this visual of what you're doing, what's actually happening on there.